Okay, so good afternoon, everyone. Today we have a distinguished guest from India, Professor Gobinda Majumder, who is going to report about Indian neutrino program. So we have our own neutrino program here, so I think it's very nice to hear about neutrino program in India. So please welcome, and I remind everyone, if you have questions, please raise your hand. I will come with a microphone.
Thanks, friend of JINR. And compared to the JINR neutrino physics program, Indian program is very, very small and tiny. I will just tell that what we have done last many years, or the present what it is. Again, I am repeating, compared to this JINR many neutrino physics program, this is very tiny amount. So I will just give you some historical background, and that's actually the only we can proud of that historical background, what we did earlier days, and then talk about the recent past, actually where I spent more than half of my scientific career, but eventually output is nothing. And then we will talk about the little bit of present activities, what are the other small activities is going on in India in the neutrino part, and in the future direction where we are planning to go. So, as I said that this is the Indian neutrino program. It started with an accidental initiative of the neutrino program through the muon lifetime. And you may know this is Dr. Homi Jahangir Bhabha, which is as from the name of the Bhabha scattering. And he was our founder directors. And in 1949-50, and he has a student, B.B. Srikantan. He became later on our director of our institute. When he joined as a student, Bhabha told him to make a simple setup, cosmic muon with the magnetic field, basically to measure the muon lifetime of the mu plus. It is in 49-50s. That time the muon lifetime was not measured that precisely. And Srikantan made this instrument to measure the muon lifetime. And that time, just after the Second World War, not many equipment is found. And I was told that Srikantan used to go to this local market, is called this, in Indian language called the Chor market, Chor Bazaar. That is basically where the black market things are available. So he used to buy some old discarded military equipment, the old days vacuum tube and others, and there is no written documents. So here they have to break one of them, find what it is, accordingly they have to make the instrument. So using that, he made this device to these proton lifetimes, but muon lifetime. But by that time, the muon lifetime was measured in the West. So this project was almost failed. Then Bhabha told him, okay, you made this instrument so it can detect the muon. Go to this Kolar Gold field. This is this gold mine in the southern India, and where we eventually went to much deeper, but initially he said that go to the Kolar Gold mine. There in the different depth, measure the muon flux rate with the instrument. So that's the starting, we say that cosmic muon at the underground, and in 1951 start the Kolar Gold field activities, and this is the seat for the neutrino physics program in India. And this is actually the mine shaft, and actually I am once in 1992 they closed this. I went down to 2.3 kilometers with this shaft in the underground facility where most of the experiment went on in the neutrino, or this muon experiment went on in last 40 years in India. So in there, they using very simple technique they use. The electronics they use some other thing, but for the time they use the Geiger-Müller counter and put in some of the shielder in the two sets of Geiger-Müller counter layer, they measure the muon flux. And this is the depth versus the vertical muon flux, where they went up to the only 270 meters. And this is the, as I say, Geiger-Müller counter telescope used for this muon measurement. And always ups and downs. And when we found this is a place where we can make our experiment, and that time this gold mine company, they do not find this much profit, they want to close it. But luckily that time they initially by the state government and finally by this government of India, they took the undertaking of this mine, and it was continuing for some more years. And in that directions, so this main KGF cosmic ray muon experiment is started. So in series 1961, series of cosmic muon experiments started in TIFR. So it go for the 270 meter to 2760 meter down very deep. And in that deep, they measure the muon flux up to the almost 800 to 900 hectograms per centimeter that below. So this story is again here. This when they go for this 2760 meter muon flux at the depth, the meters, when they put these devices, they do not see any signal for a month or so. Then these people that strike that, okay, we do not see any muon, so that means that is the place where there is no cosmic ray particles, and that the place can be used for this neutrino experiment. And based on that, this is the proposal came. This is the Menon. He was our second director of the TIFR, and this is this third director, and this is the another physicist in the institute. They write this, and also by that time that Miyake from this Tokyo University, they also joined there. They write these proposals. They say that this is the ideal place to carrying out the experiment, study the cosmic ray. The 2.7 kilometer, there is no lab was there. At present also there is no lab at that depth. And also this is not the mountain, this is the horizontal plane 2.7 kilometer, is the muon flux is reduced substantially very, very small. And improve the lower limit of the proton lifetime they can do, and probe the existence of this intermediate vector boson. This is, we are talking about the 1963. So that time our standard model is not established, it just came out. So they said that we can measure all these things. And actually this paper started the ball rolling for the series of important experiments to be conducted at KGF over the next 30 years to study the neutrinos, and also they explore the idea of this, what we call that baryon non-conservation of the proton decay experiment. And so then the group was formed, Tata, Durham and Osaka University. Durham University also joined, and this Ulfendel from the Durham in this from university, and Miyake and his group from the Osaka University joined this experiment. And it was already known that high energy cosmic ray particles interact with the Earth atmosphere and produce pion kaon. This turns decay into the muon and neutrinos. And by that time, in Russia, at that time the Soviet Union, these two, Gregory and Vadim, they already calculated that what is the flux and the angular distribution of this neutrino. And in 1962, already accelerator based experiment, they found that nu and nu are different. So all these inputs allowed the KGF group, this is a Kolar Gold field group, to estimate the expected rate of the neutrino interaction underground and to optimize the size and type of the detectors required to detect them. So a long tunnel of roughly 2.3 meters at 2.3 meter depth at this Champion Reef mine, that what is this, I show the lift of that, which was chosen to the site for this experiment. And it was done in this different stage. That time it was very simple setup. This is this scintillator detectors which is used for the triggering, and the neon flash tube to track these trajectories. This was the different, gradually it goes in the different of this one by one, it increases. So this we say that telescope 1 and 2, if we go back, this is basically in this telescope. This telescope was made earlier, then slowly this and this telescope was made, and they were made in 1965, 66, 67. And if you see, this is this plots I showed, this is the depth of this depth in meter equivalent waters, and what is the muon flux. This is the muon interact per meter square per stereo per year. So this is the Kolar Gold field. This was the facilities where this was roughly 30 muon per meter square per year. But that time also for temporarily, there was a small experiment was set up in the South Africa, in this South Africa again gold mine by these Rhines. And these, the Kolar Gold field and Rhines, they were the competitor at that time, but somehow Rhines lost the bed with this Kolar Gold field. So this is the Kolar Gold field, this is the experimental setup. Rhine has the different kind of experimental setup with the scintillator detectors where they put the different layer of the scintillator detectors. But these KGF groups, they submitted these papers for this observation of the neutrino in the 12th July, but whereas this is the Rhines group, they submitted 26th July. By 2 weeks, they were loose to the Indian people. Okay, so that's always we say that even though this is a very small number of people, this very simple technique they use, but they beat the Nobel winners at that time. And actually this paper was published in the 15th August 1965. That also another famous thing, then 15th August is our Independence Day. So this is always, we everywhere, anytime we say in high energy physics, always show these papers and compare with the Rhines papers. Okay, so this is the neutrino, and actually that time, this is the pictures of some of these events which was shown is seen. And still now, PDG carries that word. This is the latest PDG, if we say 2024. It's the first detection of the atmospheric neutrino as reported in 1960s by the underground experiment in the Kolar Gold field experiment in India and in the South Africa by the Rhines. And actually that time, there was many interesting things was seen in the Kolar Gold field. There was a few events were seen. We see the trajectory of this in the event, and if we just pointing the trajectories of these tracks, it pointed in the free space in the cavern, not in this rock or these materials. And there's a few events, it was known as the famous Kolar events. And if we calculated this free space in this area, and that time it was speculated the decay of some long-lived particle of mass around 2 GeV of lifetime of the 10 to the power -9 second, but later on this was not established in these larger experiments. Then this experiment was continuous a little more, this KGF Kolar Gold field experiment, and eventually it was made of the 140-ton detector. This is the simple proportional chambers. Both the two perpendicular directional alternate layer of proportional chambers was used. This is iron-based iron as the material, and the proportional counters used to detect this. Mainly this was made at that time neutrino as well as the proton decay. At that time the proton decay was, this was the very famous, people are speculating the proton might decay, like this Kamiokande and other experiment. This was also one experiment was done. We have some signals, but these are not this, we did not see the protons. And at that detectors we see the atmospheric muon flux, and then when this zenith angle is very large, this was identified as the neutrino induced the muon. And actually these detectors attracted lots of people. This is again the historical story. In 1979, when the Abdus Salam, they received the Nobel Prize, and afterwards India government requested him to visit the India. So one of the condition was that if he allowed to visit the Kolar Gold field, he will come to the India. So that's the things at that time he visited. This is the Abdus Salam, and this is the Professor Srikantan. I say that that time he was the directors, and he is the V.S. Narasimham, who was in charge of the Kolar Gold field. And this is the another person is Professor Nama Mandal, who was later on took the charge for the India-Based Neutrino Observatory. I will come to that points after that. Okay, so then in 1990s, this gold mine looks like is not profitable. So this government say that we will close this mine. And physicists tried to keep these facilities. And as I said, this is a 2.7 kilometer underground facility in this horizontal surface. It is very demanding, but somehow we did not get the proper support from the government or other Indian community, and we had to close this KGF activity. And that's, to me, it is the huge loss of Indian high energy physics community. Okay, so let's go to the old story. And then after that, in around 2020, and that's the year I returned back as a regular member to the institute, in Tata Institute of Fundamental Research. There's another initiative was started, what it called this India-Based Neutrino Observatory. And this has a multi-layer goals. So first thing is the determinant of the neutrino mass ordering, independent verification of the neutrino and antineutrino, detection of this matter effect. Then the measuring of the neutrino properties, mixing parameters, non-standard interaction, CPT violation, decay, decoherence, sterile neutrino study, long-range interactions, and earth tomography. Third is the search for this physics beyond the standard model, beyond the neutrino standard neutrino physics, magnetic monopole, long-lived particle, dark matter annihilations, and also act as a long-term detector looking for the atmospheric and astrophysical phenomena, searching for the unknown, and that might help for this multi-messenger astronomy. We have this other astronomy also, so this combining with this setup could be a part of this multi-messenger astronomy. And then this is this underground facility, radiation-free lab infrastructure useful for other experiment, high energy physics, biology, material science, geology, readiness for the future opportunities, and also a large scale experiment running in India for the development of experimental physics, human resource, development of the expertise, educational training hub for the students. So with this goal, we started this project called this India-Based Neutrino Observatory, and one of the flagship experiment is this iron calorimeter that was supposed to do this neutrino mass hierarchy problem. And this picture was something like this. If you see this India, this is the southern India. Southern India, there is one town is called as Temple Town, is the Madurai. From there about the 100 kilometer west, this is the Bodhi mountain hill, and this is the pictures of this mountain hill. And we are planning to do, this is from this surface, we go roughly 2 kilometers on the tunnel, and where we will go down from the peak roughly 1.5 kilometer below the mountain peak. There we should have this our underground facility, and facility was initially planned was roughly this. We will have a space for this 50 kiloton iron calorimeters, and also have a space extra 132 meter long space to extension of it. There is a space for the neutrinoless double beta decay, and also a space for this dark matter search, and there is also one space was kept for this, produce the materials for this neutrinoless double beta decay under in the depth radiation free zone to produce the materials there. So in this area, we are supposed to have the 50 kiloton magnetized iron detectors, and this is also very simple design. This is iron detectors, these alternate layers of this iron, and RPC are the sensitive detectors. But okay, very beginning I say that at this project, at this present, this project is completely stalled. It is not officially closed, but we are not getting any fund for this. And as I said that this project started in 2000 initially, but eventually it take this speed in 2005 or 6, but it went up to 2023. And initially Professor Nawamandal, who was in charge of this project, and in the later phase I was looking after this project. Okay. So at that time, what was our calculation? We say the calculation of this neutrino mass hierarchy, if it is a normal hierarchy or inverted hierarchy, we need roughly 10 years to get the 3 sigma significance. And when we made these proposals, that time initially the project was full 500 kiloton detectors was supposed to start in 2014, and by 2024 we should have this result. And at that time in this horizon there is no experiment was there to measure the mass hierarchy. And also there is another thing, these detectors was planned to use the magnetic field, and there is no other experiment at present in underground facility with a large detector with a magnetic field. Okay, and also some more things we say that how much we can measure the neutrino mass parameters and the CP violations with this, including the other result or only with this our INO experiment. So all these were the history, but to do that we developed completely the RPC detectors. This is one of the 2 meter by 2 meter RPC detectors, and to have these RPC detectors we developed our home built. This is the high voltage power supply where we need roughly 5 kilovolt plus minus 5 kilovolt power supply. This is this back end DAQ systems which was supposed to put at the corner of the RPC, and the front end board by the Unuspras chips. It was also developed in India, and we made this both this Unuspras of the INO chips, using the INO chips, we make the front end board. This is basically amplifier plus discriminators and with some OR gate to use for the triggering the signal. And of course, also we developed the closed loop gas system to run this big, roughly 30,000 2 meter by 2 meter RPC detectors closed loop gas system were developed, and we developed the TDC chip also in one of our institute to develop the TDC chip for this. So actually the RPC, it was a long story. We started this 12 layer 1 meter by 1 meter RPC stack. Its first operation at 2007, but still it is operated, still we are keeping this RPC as operational, and this was used initially just to look for this RPC for ICAL. Then we look for this RPC for the long term stability of this RPC made in the Indian industry, and then it is used for the student training, and also this all the electronics what we developed, this RPC was used for the test bench of these electronics. And this is slowly we go for this is the non-magnetic field, then 1 meter by 1 meter RPC we made, where we use the 500 ampere turns current. Using that we made the 1.5 Tesla toroidal field, which is the field we are supposed to have this in final ICAL detectors. Then slowly we go for this 2 meter by 2 meter RPC without magnetic field, and eventually we had this stack called this mini ICAL. This is has every features of the supposed to have the ICAL experiment. All the electronics was used what was designed for the ICAL, and this was mainly built to test these electronics run in this 1.5 Tesla magnetic field and in the stray field where my electronics are there. And it was operational in 2018 to 2023. And actually this is RPC detectors never used for any tracking purpose. This is mainly used for the triggering, but we have shown, this is the top few pictures we are showing for this non-magnetic field. This is the first one is this RPC, we have these detectors, sorry, where you go. These RPC detectors, when you have this is we have the strips along this direction and strips along the perpendicular direction. So we call that, let's say this is the x and this is the vertical z, so the xz view, and the other is this yz view. So that's the things we say that straight muon trajectory we see. Of course, sometimes we see this large multiple scattering of the muon. And when you put in the magnetic field, there we see this magnetic field is this, we see this in the x-axis, the track is bending. So you also notice the bending of the trajectory. But of course, these detectors, lever arm was not very large compared to what is supposed to use for the ICAL experiment. And also this position resolution is very poor compared to the standard gas detectors. But still, with this data, we could measure the magnetic field muon momentum about 1 to 3 GeV. So actually the one of this paper was published. And main point is there is no measurement of cosmic muon flux near the equator, and which can be an input to the atmospheric neutrino event generator as well as the hadronic models of the cosmic interactions. Though this data quality is not good, still we are trying to make some scientific input which can go of these hadronic models to predict these cosmic neutrino interactions more precisely. And actually this is this when this experiment was going on, and that time the Professor Honda was still alive, and actually he was encouraging us to give some input such that he can get this better prediction of the neutrino flux in our area. But unfortunately, he is also no more, and our experiment is also not there more. And this experiment, I say that for this large experiment, we do not have that many human resources. So when we started this project, immediately in 2008, we have a separate graduate training program to train these people who can develop this neutrino experiment. This program went up to 2023. And actually during the summer, there were dedicated summer training program, 2 weeks to 2 months, as well as many semester-long projects. Though this is closed, we do not have any money to support this graduate training program, but this is still we continue this activity. And actually this is the same stack. Actually this picture was taken I think 2 weeks back, when this is some of these young students, they visited our lab. We are trying to explain that what is this, what we are doing and what are we going to do. And these pictures I will show again, these stack pictures I will show. And here is some other pictures of the earlier days, when in the summer, roughly most of the summer, we used to have 15 to 30, that many students visited in our campus, and we try to train them. And actually these are most of them are the master students, and many of them after the training they went abroad or in the different lab for this future. Okay, so that is also history now. Now I will go for the very, at present, what are going on in India. So we do not have any big underground facilities. Only one small underground facility was there. This is again Indian map. If you see here, this is the uranium mine. But the uranium mine, it was mainly at the depth of the only 550 meters, and then another depth of the 880 meters. So when this iono cavern was not available, or we could not make this cavern, so we thought that we can use this, and then this is not useful for the final dark matter experiment or neutrino experiment, but start with this in the small scale to measure this, what is this, for example, muon flux, what is this radiation dose. Those measurement was done, and actually there is a few nuclear physics experiment was done, which this much of suppression of this muon flux at the surface that helps to get some of the nuclear physics result, which was published in these sites. And actually at present, we are trying to have a cavern which is roughly an 1.2 meter down, 1.2 kilometer down in this area. But this is in India, this is the one of the simplest or a realistic scenario that we may have this 1.2 kilometer depth cavern, but only one point is that this cavern will be vertical shaft, and in that shaft we cannot take this big material, means shaft has to make big, and that we did not get the permission to get the wider shaft. Only the small scale experiment we can do it here. So this is one setup, and another setup was running. It's called the Indian scintillator matrix for the reactor anti-neutrino. And this is, as you know, that the RAA, that is the anomaly of the neutrino rate. What you are supposed to get, we see the slightly smaller, and we speculated that is the fourth neutrino, who is mixing with this, our first generation's neutrino. To study this, we have a reactors. This is at one of our sister concerns, this Bhabha Atomic Research Centers, where you have the 100 megawatt thermal reactors, and we put a detectors to measure the RA at 18 meter distance. And the detectors is also again very simple detector. This is the plastic scintillator of 100 centimeter by 10 centimeters, and total volume is roughly 1 meter cube and 1 ton by weight, 18 meter from the center of the reactor core, and wrapped with the aluminized mylar foil coated with the gadolinium, and 10 centimeter lead and 10 centimeter boronated polystyrene for the shielding, and detector shielding to test the movable base. This is the movable base. And DAQ systems also we took very simple. Digital DAQ system on the same CAN digitizers, pulse processing and triggering, and 16 channel read from this digitizer board, and this is the 500 megasamples per second, and this is the date times less acquisition, this is the continuous data taking. And these were for this reactor, we are expecting to have roughly 60 neutron per day, 60 event per day. And this is the first result. Okay, this is some pictures of this event. This is a simple scintillator detectors with the photomultiplier in the both side, and this is the detectors pictures. And the detectors is taken some data and measured the neutrino flux. This is only about the 40 days on day, reactor on days, this data, and this is the more or less matches what is the neutrino flux we do expect this from these reactors. And another goal, it is the previous one is running. This one is the planned one. This is the coherent elastic neutrino scattering. And this physics I do not need to tell, that you know that importance of this. So this was planned to make 4 planar p-type coin contact high purity germanium detectors of mass roughly 2.4 kg high purity germanium per crystals. Threshold energy is 150 electron volt, electron equivalent, and electrically cooled to the 77 Kelvin, that is this liquid nitrogen temperatures. And again, this is the simple front end electronics, and surrounded by the sodium iodide thallium detectors of the anti-neutrino Compton shielding. And these detectors is the proposed that initially the detector will be tested at this 2 megawatt thermal power on the reactors, but eventually it will put with the another atomic power stations where you have the power station of the 2.1 gigawatt hour thermal power, and there the detector will be put in 30 meters from the core, and the time length for the installation of these detectors is 2028. So these are these 2 minor neutrino experiment is going on, but we lost this India-Based Neutrino Observatory in the southern India, but we did not keep hope to have another cavern in futures. So actually since 2021, we are trying to look for this when we more or less realize that the Iono cavern we will not able to get, we have to look for the alternate site. We try to search for this search for a deep underground experiment facility for the high energy and the nuclear physics, including the INO-ICAL with the updated physics goal. So now if we say that INO detectors, ICAL detector for the mass hierarchy, nobody will give any fund, because now the many experiments are there. But we have the upgraded goal, we have to shift it. This is the ICAL we are supposed to shift with the updated physics goal at a depth of 1.2 to 2 kilometer, and this was started in 2021. Actually, all of these are, the next slide I'll show the map. All these sites of the northern Himalaya, the northern part of this India and the Himalayan sites. Initially, we look for this all possible, roughly 20 of this position. 20, mainly we try to look for where the already existing tunnel are there. We just bypass it, or this is there's a plan that we will have a tunnel or some other option is there, because this India government will not give us the fund to make and complete one tunnel. So based on that, we look for this, all these 20 sites was selected. Eventually we visited most of the sites, and eventually we selected 3 sites. And actually at that time this INO still active. They approved that first preference, and feasibility of the other 2 sites is also going on. And actually not only this site visit, we have the regular meeting, and the first meeting on that was happening at TIFR in that August 2022 to gauge the interest of this high energy and nuclear physics community in India, which was attended by the roughly 800 participants in the different institute, and they have the different 7 proposals. I will come to that point. And also there is a several small meeting event. Last November, we had a meeting in the academy meeting where also we included the biologists and geologists. There is now I see this compared to the high energy physics, biologists are much more interested to have the underground facility. They want to see how this genome, everything is developed where there is no radiations. And of course, and also India government recently asked us to make a document, what is our visions by 2035, and both for the nuclear physics and high energy physics community, they emphasizes that we must have an underground facilities to do the different kind of physics. And as I said that this is the different sites. If you see the Indian map here, and this is the most of the site here what I am showing, this is the site in these regions. We look for these sites. Still, these sites, nothing was finalized, but nothing were abandoned. These all are in the hold. And okay, this is some of the pictures where we visited. We took basically this is the point we say that this is already the tunnel is there. We may have to take a small bypass where we can go the depth up to more than 2 kilometers. And here is some of the detail of the 3 more interesting sites, but main drawback of these sites this is the seismic zone, and that was one of the major problem we are facing. Before this, up to 2020, we always try to go in the southern India where these mountains are old, much stable. And here, this is once in the seismic zone, and also the Himalaya, the mountains are new, it is not that stable. That was one of the bottleneck that to getting the permission to have the new tunnels in this Himalayan area, but we are still trying for it. And this is the proposed experiment in the underground facilities. So we try to have this covered with one of these big underground facility to have this ICAL kind of experiment and multiple small cavern. And some of the experiment may require the clean room, so you will have the clean room facility of 100 to 1000, and projected powers will require roughly 5 megawatt, and of course water consumption and other facilities are needed. And actually when you look for these different groups, they have the different kind of physics they want to do. Atmospheric neutrino, solar neutrino, neutralized double beta decay, dark matter, low energy underground accelerator in the neutral astroparticle physics. So this is actually the nuclear physics community. They want to measure these few of these low cross sections process, which they cannot do in the surface because the cosmic muon background. They want to put an accelerator and do the nuclear physics. And the rare nuclear decay, and of course the earth tomography, seismology, biology. As I told that, unfortunately, site selection is the most difficult job. So I will talk about the one of this project, which we are doing some R&D, which other than this our ICAL experiment. Okay, sorry. Before that, I just say this is the underground facility. We know that it will be hard to get, and we may have to wait for a long time. But by that time, can we make a facility where we just use this cosmic muon veto detectors, just vetoing this cosmic muon? Like the Juno detector also is veto. So that's this one of this R&D we are doing, not the R&D, just to see this feasibility study. This is the same, my 12-layer RPC stack, what is operational. On top of that, we put these scintillator detectors. These scintillator detectors we got from this Fermilab, and the readout by these photomultiplier tubes. And using that, basically we say that RPC detectors, when the muon pass through, we can identify which direction from where the muon pass through. Then we see the scintillator detector, do we see a signal or not? Using that, we give the veto of this event. So that's the way we're trying to establish this veto detectors concept. In this shallow depth, we may use it, but in this deep underground also, we may use it to reduce this background even further. So this is the one R&D still we are continuing. And other R&Ds with this a new idea, we call this deuterated liquid scintillator detectors. Okay? So this is a kiloton scale deuterated liquid scintillator added with gadolinium. So this simple concept is, let's say we have the SNO experiment. They use the deuterium and this heavy water. The signal was coming from the Cherenkov signals. But instead of Cherenkov signals, if we have this scintillation detector, then we can reduce the threshold very small. And in this deuterium, all kind of neutrino can interact, both the charge current and neutral current interactions, and the production cross-section threshold is very small. In this SNO, the main problem was that the Cherenkov detectors, that's why the threshold was high. And also when you have the gadolinium doped, then the neutron we can detect much more easily. So then we can detect all these processes with very low threshold. And so this is one of the concept we are now at present we are looking on it. And this is one of the advantages again here, that with India we have one of the largest producer of the heavy water. Availability to the deuterium is not a problem, that we are assuming. So this concept is that consider the liquid scintillator where all the hydrogen will be replaced by the deuterium. So that's this project we are trying to do, and deuterated liquid scintillator will be sensitive to all neutrino flavor, therefore it can see both charge current and neutral current event. And SNO experiment could exclusively establish neutrino oscillation by observing the both charge current and neutral current. However, it could not do counting the experiment. Here we could do, and also observing the neutral current, both the neutral current and charge current event provide this better way to measure this PMNS matrix. And as I already mentioned, small scale experiment will CN D2N is established that R&D is going on. And one of this main target of this unique selling point, we say, there is solar neutrino. We see the neutrino surviving probability. This is a theoretical model, and these are the defined experiment. But there is no measurement roughly from 2 GeV to the 7 GeV, no measurement are there. Theoretically, we are extrapolating from this to this. And if you see the deuterated liquid scintillators, we can probe in this region also, we can have a point here, just to verify that in this region is really the P goes like this way or something extra effect is there. And of course, also this will do the supernova neutrino. We can reduce the threshold, so any kind of supernova neutrino in the low neutrino threshold we can see. And here is the sum of the pictures. We show that if we see this supernova neutrino with this low intensity or low or high, it was the all things are given in this reference. Basically, how far for this supernova from us, how many of the neutrino we can detect, and also we can say that if we detect the neutrino, what is the energy of the neutrino, what is the energy of the neutrino, if this flavor equilibrium or the no oscillations, then we see some difference. Using that, we can understand this how the supernova neutrino produce, what happened at that point. In this setup, we can distinguish this flavor equilibrium or no oscillation scenario. Okay, so these are the things we are trying at present, but this is the huge task. We just started with this project. I think that's the things we have done. At present in India, we do not have the much to say. We say that we had a golden period of the KGF era and spent 2 decades for the INO project. And at present, looking for the alternate site for the future running facility in India, and in parallel having a small scale reactor-based experiments. And as I said that we are having this tradition to train the student, and we organize the many school for train the student, and this is the one of the school we are going to organize in the next year, January 11 to 30th, and this school mainly to train this student, which is this final year of the masters or the first year of the PhD program. And I request you people to look on this abstract, and if you are interested, please apply for the as a student. And for the seniors, I have a defined communication with them how to collaborate for this school. Yeah, with that, I stop here. Thank you.
Thank you very much. Okay, please, questions?
Thank you, Gobinda, for coming here and giving us a very comprehensive recent history of neutrino research in India. I have 2 or 3 questions, if you don't mind. I'll start with the first one. So, from your talk, of course, it's very evident that INO project not being greenlit is a big loss for the entire neutrino physics community in India. Could you tell us any detail of why it did not go through? Was it purely financial reason that the Indian... So there are other extenuating factors?
So this is not the financial reason, okay, this is, okay, don't go to the outside the room, this is a political reason. So we went to a state which always objected anything the center is proposing.
Okay, so it was an objection from the state side?
State side, okay. Particularly Stalin.
So the land acquisition, permissions, etc. were
that's the things. Money was not an issue, we had this, money was sanctioned by the parliament.
Okay, good to know. What happened at Jadugoda? You mentioned that that of course is already a mine, so you needed more depth to build another shaft, but it did not get permission for a wider shaft kind of thing. What was the reason? Was it like safety reason? What sort of issue?
In general, if you look for any of these large scale experimental setup, everybody go for this horizontal path to take this load and others. In general, for this big shaft, it is this safety concern or making it is very difficult, that as far as I understand.
But so, that brings me to the other question. Now that you mentioned that you have sort of primary selection, very early selection of 3 other regions, all 3 are in Himalayan region, that's yourself said it's a seismic zone, so it's more dangerous, and you have to start from 0. Whereas if you have a mine, you are not starting from 0.
No, so this, if you say this mine one, I would say Where was I? Okay. Already this place, there is a small experiment is going on, that is there, small lab. We can go up to this, there's already shaft is there. But if you have to make this to, another shaft, which is completely new shaft, not linked with this.
Ah, okay.
Completely new, not this, not linked with this.
I see.
So that was the point.
But then why are you, or not you, the community, the committee that's looking for sites, why are you looking in that Himalayan region? I mean, why not somewhere else, which is not a seismic zone?
We exhausted all the site. Okay, let's say there's a 20 years back when we first looked for the site, Himalayan site was rejected because that was the seismic zone. We looked for all other sites in the South India, and we did not find any sites where we can have more than 1 kilometer height. So that was the point. We did not find any sites in the southern region. That's why you have to again.
Was it purely you could not find a site, or was it again some other factors?
No, we could not find the sites more than 1 kilometer.
No
Maybe
mountains?
barely on 1 kilometer we may have, but we do not say. Okay, Tamil Nadu, the state, there they will not give us the land that we realize now. And so this maybe in the Tamil Nadu 1 or 2 more sites are there about 1 kilometer, but we did not look. We looked for the Andhra Pradesh, Gujarat and some other places, and we did not find any place.
All right. And my quick last question, so since it's sort of frustrating for Indian neutrino physics community because you don't have a proper place, are there groups in India, collaborators in other like international collaborations and neutrino experiments? What are the activities from there?
Yes, so these Indian groups, there is a groups, they work for the NOVA and MINOS experiment. And they are planning that the same group will join in this Dune. And in parallel, another group is trying for the Hyper Kamiokande. But after coming here or before here also we discussed, we do not see anybody is shown interest for the Boikal GVD. Let's see if what can I do for the, yes, I'll try it.
Yeah, other questions? Comments? I have a question regarding this last proposal with gadolinium doped.
Yeah.
What is the mass of the detector you're expecting?
Sorry?
Mass of the detector.
That's the, initially we said the 1 kiloton, we'll say, but finally it is this, just a minute, initial goal is started with the 1 kiloton, but then depending on this, it will have to increase. Okay.
So do you have already developed techniques how to make this scintillator with deuterium instead of hydrogen?
So basically this, we are trying to see this, we have these scintillators, we are trying to replace with the deuterium.
Yes.
So we did not succeed yet, but this is this ongoing project.
Is it an easy job or really
I do not think it is an easy job. That we could have done by this time. Yeah, it will take some more help from my chemistry colleagues.
The idea is interesting, but I never heard that anybody succeeded doing this.
Yeah, so that's this one plan.
Okay. Any other question, comment? Okay, if not, then thank you very much for coming and sharing with us.